Have you ever wondered about this question? How can a computer, something without neurons, without consciousness, and not even capable of thinking like a human, judge right from wrong, calculate complex formulas, and even defeat world champions at Go? You might never guess that all its intelligence actually comes from the most ordinary physical phenomena in our lives, the high and low of voltage. It sounds incredible, doesn't it? But that's the most amazing part of the computer world. Between the simplest electrical signals and complex intelligent behaviors, there's only a bridge called logic. Today, we'll start from the most fundamental physical principles and break down step by step how the first thought of a computer grows from electrical signals. To understand a computer's thoughts, we first need to start with the most basic concept, electricity. Connect a wire to a battery and a light bulb. The moment you press the switch, current flows along the wire, and the bulb lights up. When you turn off the switch, the current is cut off, and the bulb goes out. In this process, there's a key physical quantity that changes voltage. And have you noticed? This naturally results in two clear, stable states. Electricity present can represent 1. No electricity can represent 0. There's no vague middle ground. Just like the two sides of a coin, one or the other, no in between. It's this simple characteristic that allowed computers to find their own language, binary. Computers don't need to understand the tones of Chinese or the grammar of English. They only need to transmit and store information through the high and low voltages in circuits. The hello world we write in a computer's eyes is actually a binary code string dozens of bits long. Every single 0 and 1 corresponds to a low or high voltage pulse in the circuit. This is how computers understand the world, simple yet extraordinarily reliable. But here's the catch. Being able to represent just 0 and 1 is far from enough for a computer to think. It's like having letters but no grammar. You can't form sentences. For a computer to make judgments, for example, if the temperature exceeds 30 degrees, turn on the fan, it needs a component that can control the on or off state of current. That component is the cornerstone of the computer world, the transistor. If we imagine current as water flow, then a transistor is like a valve. It has 3 key interfaces, the base, the emitter, and the collector. When we apply a high voltage to the base, this valve opens, and current can flow smoothly from the emitter to the collector, just like turning on a faucet, allowing water to flow out freely. If there's no voltage at the base, the valve shuts tight and no current can pass through, similar to turning off a faucet, stopping the water flow completely. From this, we can derive a logic rule. If there is electricity at the base, condition A is true, then electricity flows at the collector. Result B occurs. Does that sound like a logical statement? Exactly, this is the logical foundation of computers. A single transistor is the smallest thinking unit. It can only make yes or no judgments. But when there are enough of them, their power becomes astonishing. A CPU contains tens of billions of these electronic valves. They open and close at a rate of billions of times per second, switching between high and low voltages to complete logical judgments one after another. This is the physical essence of a computer's thinking. Now, with transistors, we can combine them like building blocks to form more complex logical structures. These are logic gates. They are equivalent to the grammatical rules in a computer's language, taking multiple 0 and 1 inputs and outputting a definite result based on fixed logic. Let's first look at the 3 most commonly used basic logic gates. A gate, made by connecting 2 transistors in series, it has 2 input terminals and 1 output terminal. Its logic rule is strict. The output is only high voltage if both input terminals are at high voltage. If even one input is low voltage, the output is low voltage. It's like needing both a key and an access card to go out. You can only open the door if you have both. Missing one won't work. Or a gate. Composed of 2 transistors in parallel, its logic rule is more flexible. The output is high voltage if at least one of the 2 inputs is high voltage. The output is only low voltage if both inputs are low voltage. This is like having 2 lights sharing a main circuit at home. Turning on either light switch will complete the main circuit. The main circuit is only broken when both lights are turned off. Not gate. The simplest in structure, it has only 1 input and 1 output. Its logic rule is inversion. If the input is high voltage, the output is low voltage. If the input is low voltage, the output is high voltage. It's like a mirror that always reverses the state of the input. This provides the crucial inversion capability for combining more complex logic later. These gates seem simple, but they can construct all types of logic. Let's take an example. If the weather is sunny and today is a weekend, then I'll go for an outing. This is essentially an AND logic gate. Computers are constantly performing this kind of logical judgment. They use circuits to replace the yes or no thinking our brains do, and logic gates are the most basic grammar in the world of O south and 1 south. So what happens if we combine multiple logic gates? The answer is, we can make machines perform mathematical operations. Take the simplest addition circuit as an example, the half adder. A half adder is designed specifically to calculate the sum of 2 1-bit binary numbers. It consists of 1 XOR gate and 1 AND gate with 2 inputs, addend A, addend B, and 2 outputs, sum bit S, carry bit C. The XOR gate is used to output the sum bit. The AND gate is used to output the carry bit. Let's calculate 1 plus 1 in binary. Addend A equals 1, addend B equals 1. The XOR gate receives identical inputs, so the sum bit S equals 0. The AND gate receives 2 1 south as inputs, so the carry bit C equals 1. The final result is the binary number 1 0, which corresponds to the decimal number 2, exactly the same as the addition result we're familiar with. If we combine two half adders and add an OR gate, we get a full adder. Unlike the half adder, a full adder can not only calculate the sum of two 1-bit binary numbers, but also accept a carry signal from the previous bit, enabling multi-bit binary addition. When we combine thousands of such full adders and half adders, along with logic gate circuits for subtraction, multiplication, and division, we can form the computer's arithmetic logic unit. This is the computational core of the CPU. All mathematical operations and logical comparisons rely on it. So, in essence, a CPU is a massive circuit network formed by layering logic gates upon logic gates. Every time you press the Enter key on your keyboard, thousands of voltage changes flash inside the CPU. They follow the same Boolean logic, turning thinking into the flow of electricity. This is the complete process of a computer thinking, converting human needs into the flow of electrical signals, and then outputting results we can understand in accordance with the rules of logic gates. When we look back, a computer's thinking is nothing more than billions of transistors switching between being powered on and off. But it's this simple combination of 0 and 1 that allows computers to recognize images, translate languages, and generate music. You could say that human neurons transmit information through chemical reactions. A computer's neurons communicate through electrical signals. Both are doing the same thing, using logic to build intelligence. So the next time you press the power button, what you're lighting up isn't just the screen, it's the miracle of logic and electricity. In the next episode, we'll continue exploring this miracle. How do computers use 0 and 1 to translate human symbols like text, images, and sounds into electrical signals they can understand? See you next time!